Alright guys, for part 2 of our video on the law of signs, we talk about what we call the ambiguous case. Okay, the word ambiguous literally means not easily defined. Okay, so you're going to see why that is when we talk about what the ambiguous case is. And we're going to start by thinking back to our geometry class again. We had 5 different postulates that we used to prove two triangles congruent. Side, 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 side angle, side angle, side angle, 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 side. HL was for right triangles. I know we're not dealing with right triangles in this class, so there were 4 in that case. Your geometry teacher would have also told you that there was one that is commonly mistaken for a way we might be able to prove two triangles congruent, and that was our side-side angle case. Okay, so basically, if you were given two sides and the non-included angle, we could not prove those two triangles congruence. Now, at the time, we probably didn't go through with you, and I teach geometry. We don't necessarily go through why that's the case. Okay, maybe until later in the year, and even then we don't spend a lot of time on the ambiguous case. Okay, but the reason is this. Okay, if we were given the length of two sides, let's say that one of those sides I'm going to draw like this. It happens to be, I don't know, 10 inches. Okay, and let's say the other given side was 9 inches, and the one given angle was 62 degrees. Okay. Now we can draw this, we can kind of sketch this out. And the way we would normally do that, to sketch out this triangle, okay, with 3 given parts where we don't know the third side or the other two angles, we can kind of use like a dashed line here to really set the given angle measure. Let's say that's the 62-degree angle. So I know this side is going to be along this line, this orientation, because I know I need a 62-degree opening here. But I don't know how long this side is. Okay? We weren't given this side. If we were given this side, this would be side angle side, which means we were given this other side here. Okay. Now you might think, oh, this is going to be easy. It's 9 inches long. Let me actually make this just a little longer. Okay, it's 9 inches long. Okay, that's easy. Let's just draw a 9-inch side and connect it to this. Then we'll know how long this is. But the problem is, there are actually 2 possibilities. Okay, the 9-inch side could connect here. Okay, let's say that was the 9-inch long side. Okay, but also we could connect this vertex to this line with a 9-inch side there. It's almost like we're working on like a little pendulum here. It's like, okay, this side is 9 inches long. I'm kind of using my pen to model. Well, it could go here, but it also could attach here. Okay, so the 2 possible triangles actually look like this. Which is why that information was not good enough to prove triangles congruent in geometry. Okay, it's because there are 2 possible triangles that could be formed. So if we're only given that information, we wouldn't know which of the 2 we were talking about, which means that we couldn't prove congruence from that. Okay, there's a video that you're going to see in the bottom of your week 1, semester 2, week 1 folder that has another good visual, similar to what I did, but kind of in real time. Okay, so if you're curious and want to see that visual representation of why there are 2 possible triangles when we're given side-side angle, check it out. All right, how do we deal with this? Okay, we're going to use law of signs. Okay, we're going to use law of signs to find We're going to use the law of sines to find the one missing angle measure, the one we can, okay? As if I come up here up top, if we have a side-side angle case, we would use these two, and then we would use these two to find that angle. That's where we would have to start with law of sines. There's nothing else that we could solve for first there. So we're talking about that one missing measure. It's that one that we actually could solve for first, okay? So here's the deal. After we do that, there's going to be some things that might happen, okay? If we get a no solution or an error as we're solving for this in our calculator, there actually isn't any triangle possible with that given information, and that's okay. All right. If we do get an angle measure, okay, that is going to be in our first possible triangle. Okay. And then what we need to do is 180 minus that angle is going to be our second possible triangle. And we need to test it. I'm going to talk to you about what that means here in a second. All right. And here's why it's 180 minus that angle. Those two angles, the first one that we get and 180 minus that, those represent these angles here. Those represent this angle here and this angle here. They happen to be supplementary. Okay. And when those angles are supplementary, those are the two possibilities that we might get. Now really there's three things that could happen in a side-side angle case in the ambiguous case. There might not be any possible triangles. There might be one possible triangle, or there might be two. Let's do an example and see what we mean by that. Okay? Solve the triangle. We have two sides and an angle. Let's sketch this out, and what we're going to see, for me it's always ABC, 72.2 degrees, side across from B, 78.3, side across from C, 64. Side, side angle. This is the ambiguous case. The first step is to use the law of sines to solve for the one angle that we can, in this case angle C, because we have that opposite side. So sine of 72.2 over 78.3, sine of an angle over its opposite side, is equal to sine of C over its opposite side. We cross multiply. 64 times sine of 72.2 equals 78.3 times sine of C. Now this goes back to our solving trig equations. We divide both sides by 78.3. And to solve for this angle, we're going to do the inverse sign in our calculator. Remember, when we're using trigonometry to solve for angles, we'll always have those inverse. We'll put this right into our calculator. We'll see what happens. And what we get here after putting this into our calculator, making sure we're in degree mode, is 51.1 degrees. Okay. This is our first possible triangle. I'm even going to put a 1 there. Okay. So this really is going to be like B1, B1, C1. We now have capital C1, first possible triangle, 51.1 degrees. At this point, since our first triangle was possible, we know that because we didn't get an error here. If we would have gotten an error or an undefined value here, you would stop this problem and say no possible triangles. Okay? But the second thing that we need to do, since we got one, we have to test to see if there's a second possible triangle. We're going to draw the same exact triangle with the same given information. 72.2 degrees, 78.3, 64. Okay. The second possible angle C is 180 degrees minus our first angle C. That's what we just talked about on the previous page with our notes. So capital C, or angle for the second triangle, I like to use a little subscript of 2 here, is going to be 51.1 degrees. It is we're testing here that second angle C. if this second triangle is possible, would be 128.9 degrees. This is our test to see if there is a second possible triangle, and here is what we're looking for. Does the given angle, the one we were given at the start of the problem, plus our calculated second possibility for angle C, do they add up to something 180 degrees or greater? Because if that's the case, that's impossible. Okay? We need at least some sort of degrees here for this angle. And if these two add up to 180 or greater, that would be impossible. Do they add up to 180 or greater? They do. That second triangle is not possible. So we're just going to continue to finish solving the first triangle. How do we find the measure of angle A? 180 minus these two, so 180 minus 123.3. And angle A would be 56.3 degrees. Sorry, 56.7 degrees. And then the last thing we're going to do here is use law of sines to solve for lowercase a, the side across from a, now that we know this is 56.7 degrees. So let's set up our, we're going to go right over here to do that. Let me give ourselves some room. We're going to go sine of 56.7 over little a equals sine of 72.2 over 78.3. Remember, we're using those because those were the non-rounded values. Those were the given values. So we cross multiply and divide. We'll get 78.3 sine of 56.7 all over sine of 72.2. This is going to go right into the calculator. For that, we get 68.74 Does that make sense? Smallest angle across from the shortest side, middle angle from the middle side, largest angle from the largest side. This looks really good. Now, we're not going to do any more examples here in the notes, but I want to talk about what would have happened had this triangle been possible. Okay? So remember, three options. If we would have originally solved for the first angle C and got an error or undefined value, we stop there. That first triangle isn't even possible. Okay? Our answer would be something like there is no triangle possible with these given measurements. Done. Okay? But if we do get a degree measure for this first triangle, and one is possible, we subtract that from 180 to test our second possible triangle. It might not be possible. If that's the case, we just finish up our first triangle. If it would have been possible, meaning these two angles would have added up to something less than 180, all we would have done is solved this triangle, the rest of it, the same way we would have done for number one. Okay? I like using subscripts here, so not only would we have B sub 1, B sub 1, C sub 1, C sub 1, A sub 1, A sub 1, we would have B, C sub 2, little a sub 2, capital A sub 2. Okay, these first three would be the same in both, if that makes sense. Okay? So, when we get the ambiguous case, we solve for the only angle we can. If it's an error undefined, no possible triangles, done. If we do get an angle measure, we input that. We then test 180 minus that for our second possible triangle. If it's not possible, we just finish up by solving the first. If it is possible, we finish up by using law of sines to solve for all, both missing parts of these two triangles. We'll do some examples in practice. Remember, there is that extra video if you want another little visual representation of why this is the case.